Okay, this is a collection of a few case studies that I just find to be extremely interesting. These are real world situations that I found myself in and my team found ourselves in. And these turned into really good learning experiences for us. You'll see that what we're really trying to highlight here is going to be certain misconceptions, certain pitfalls that are easy to fall into, and these things are perhaps not really intuitive to a lot of structural engineers. So I found this information to be extremely helpful. I hope you guys do as well. So it's kind of customary at the beginning of these to give some kind of profound quote from a historical figure that has some sort of applicability to today's topic. It's actually not what this is. This is just generated with ChatGPT. Nobody actually said this, but it's actually not too bad. Almost entirely useless this slide, but nonetheless, I found a way to incorporate AI into our workflow. That's one of the questions the board of directors is given me recently. Not sure if this is what they had in mind, but maybe at least it's a start. Unfortunately, ChatGPT was terrible at putting together the rest of this presentation, so I had to do it myself. So first, we're going to talk about the concrete topic, pore strips in particular. Um, This is a photograph I took on site. I was on site with another structural engineer a few years back. And at the time we were visiting this project, we didn't recognize that in this photograph, there's actually a major red flag, something that is not at all easy to spot, I suspect. I would be surprised if very many structural engineers would look at this and know what the problem is. In fact, there's two issues, one of which is potentially serious. But we're going to go ahead and come back to this photograph at the end of the presentation because I'm hoping that once we do, the problem in this picture is going to be immediately apparent, right? And of course, it has to do with the pore strip. You can see the pore strip's kind of located right here where you still have the original formwork on several of these slabs. But in any case, let's start off with just a brief overview of what a pore strip is and why the pore strips are so important in post-tension concrete design. Fully recognize that there's probably some engineers here that are not terribly familiar, so we're going to go over the basics here first, and then we'll get into some of the more nuanced details and, in particular, the issues surrounding this project. So consider for a minute this floor plan. This is really typical of what you may see in maybe a 10 to 15 story building, maybe a hotel structure. You could see that you got your shear walls kind of lining your elevator cores as well as your stairwells. So very, very typical here. And let's think about the concrete floor slab for a minute here and what we do when we're post-tensioning these floors. Post-tensioning has two purposes. The first of which is just to put a uniform compression stress into the slab in both directions, right? And this pre-compression force, or rather post-tensioning force, is very significant. So for a typical hotel structure as this, the forces you're inducing into the slab are usually somewhere around 15 to maybe 18,000 pounds per linear foot along these slab edges, right? And that's achieved just by running steel cables through the slab. You pull on them at the ends in order to tension those cables, then you anchor them to the slab, creating the compressive force. So very, very high forces running through this building. And you can kind of see, let's zoom in. You can kind of see I drew in this dashed line here what the slab is going to try to do in response, right? There's this equation in structural engineering, one of the first equations you learn, PL over AE. You apply a P, a uniform compressive or tension force into a structure or any element, and that thing either shortens or elongates according to that formula. right? So that's exactly what the floor slab is trying to do here. Now, if you look at the center of mass in the middle of this slab and you think about it, you're really not going to get any movement due to this pre-compressive shortening at that location. The further away you get, though, the more movement you're likely to see, right? So along the north and south edges here, you're going to get a little bit, but not as much as you're going to see at the far ends of the building, right? So your four corners here are kind of the locations where you're really going to see maximum movement within the slab, right? And that movement itself is not really the problem that results. The problem is that this movement is restrained in a lot of instances, especially here, right? So think about your concrete shear walls. By definition, those are designed to not really allow, or at least to resist, horizontal forces. And so they're just fighting against your slab, right? So what's going to happen when the slab shortens, and I should say it's not just the slab shortening due to the compressive force, but also normal concrete shrinkage. It's fighting against your shear walls that are pulling back the other direction. The predictable, inevitable result is going to be a series of cracks, are very likely to form. And of course, the larger the structure is, in this case, the left to right direction, the more cracking you're going to see. Now, there is a useful rule of thumb that for every 100 feet of building length, you're going to expect to see somewhere around 3/4 of an inch of slab shortening. So that kind of gives you an idea of how much cracking you're going to see as a function of the building size. But if I had to guess, a structure like this is probably going to develop some cracks somewhere in these regions first. Now, the pore strip at the end of the day is really just a way of mitigating this cracking phenomenon that is likely to occur. And so this now is an illustration of the same building, but with a pore strip introduced. So here you can see the slab is broken up into two separate pieces with this central piece left out at this point. That central strip running through the building is what we call a pore strip. So the left-hand side and the right-hand side of the building, those are poured independently. There's no connection. The post-tensioning is done independently in each one. And then this pore strip down the middle does not really get filled in for an extended period of time. So the idea is both the left and the right-hand side are going to shorten over a period of up to 60 days, but definitely at least 30 days to really be effective. And only then do you infill the pore strip. And of course, that pore strip has to make the slab behave as a continuous slab under the final configuration. But you can see here how you're really reducing the potential for cracking around our restraining elements here. So these are indeed extremely effective tools for reducing what would otherwise be inevitable cracks in these slabs. So that's the basic idea. Let's get into a couple of interesting details surrounding these. So first off, I'd like to pose a question. And this is not a test for the audience. You guys do not have to answer. But think about this. If you are designing a structure with a pore strip in it, which one of these 3 points are you going to locate the pore strip, right? And so I think structural engineers, when they think about this problem, immediately start thinking about force and moment transfer through the joints, right? Do I want to put it at midspan where I have maximum moment that has to be transferred, but on the other hand, there's minimal shear? Or do I want maybe more like a quarter point, right, at the inflection point, in other words, where the moment is zero or very close to zero? And shear forces, those can be transferred pretty readily, it seems, with just dowels, maybe at the mid-depth of your slab. Or maybe you're completely insane and you think that we should put this right off the face of a support, right, where you have maximum shear, or some other location. So instead of actually polling the audience, which I know audiences hate, I went ahead and went back and did a historical project survey. I even asked several engineers where they thought the pore strips generally should go. And we even have our hands on some drawings from other firms where I could look at those drawings and see. So combining all of this together, I kind of got a distribution like this, where most engineers are going to say that you should put the pore strip at the quarter point. Um, for reference, though, I went ahead and also, for career day at my kids' school, I asked the kindergartners to vote where they thought the pore strip should go. And you can see they obviously have absolutely no idea. They're just guessing. But let's see what the correct answer actually is. And this is surprising to most people. You really do not want the pore strip to be at your quarter point. You want it to be at your midpoint, okay? And so Miss Padilla's kindergarten class wins this round. But why is it that structural engineers kind of underperform random in this situation? And it really comes down to a couple of the nuances that I want to get into now. So I'm going to try to convince you guys why the midpoint is where we really should be putting these pore strips, okay? Now, there's a couple of reasons for this. So let's focus in on a few. So first, I'm going to give you what's really just the textbook kind of answer to why the pore strip should go in the middle. So any textbook you read on post-tension concrete is likely to point out this problem right here, that if you put your pore strip at the quarter point and then you pre-compress the two slabs, you're likely to get the slab on the short side to actually lift up off of the forms. And in fact, I have seen this happen multiple times. And the reason it pulls up in a lot of cases has to do not directly with the compression force that you put into the slab. It actually has to do with the other main idea of post-tension concrete, and that is what is referred to as load balancing. So the cables generally running through the slab are not just vertically flat cables that go through the mid-depth of the slab. They tend to drape upwards and they tend to drape downwards in strategic locations. So you can imagine these cables, as they are in tension, they are trying to straighten out. So anywhere that it's draped to the bottom of the slab, such as right at the midspan of the slab, it's going to push up on the slab at that location. And then as it drapes back up over your columns, it's going to push back down on those columns. So you're really redistributing gravity forces and offsetting a part of the dead load with that drape that you put into the cables, right? And so because of that, there's a strong tendency for there to be some uplift forces that occur at the end of these short cantilevers. Now, that's not necessarily the case. You can mitigate this by simply not draping your slabs either in the first bay here, the cantilever bay, that column, or in the next bay over. So that will certainly reduce the likelihood of it lifting, but on the other hand, you're then not balancing as much of the dead load, which in itself can be a little bit problematic or a bit of a trade-off. But the basic idea here is that the slab can lift off, and it's not hard to see how this is going to cause a problem when you come back and infill that pore strip. But the problem actually gets compounded by another effect, because at some point in the not too distant future, after this is post-tension, these forms the shoring is going to come out from underneath that slab. And so when the shores are ultimately pulled, you get this type of condition where the deflected shape in your adjacent bay causes additional uplift at the free end there. And so those two can compound each other and ultimately lead to a situation that looks something like this. This is a real photograph, obviously. I got this from a textbook. This is not one of our projects. But we have had a project or two where some kind of similar type of effect did happen. Now, obviously, for a parking garage, this probably isn't the end of the world. But again, think of our hotel example, where the finished ceiling in most rooms is generally just the underside of slab that gets painted. And so something like this is going to be immediately apparent in the hotel rooms. So if we're talking a 4-star hotel, you bet there's going to be some explaining to do when this happens here. So that's kind of the textbook reason why they say do not put your pore strips at the quarter points, rather put them at the midspan. But there's an even stronger reason why I think we should be doing this, and we're going to get to that reason here in just a minute. But in order to understand that reason, there's one more concept that I think we should try to think through here. And so the best way to understand this particular idea is going to be just to sketch out floor by floor what happens when we build this concrete tower with a pore strip in it. So here you can see the pore strip is at midspan now in this example. And let's just think through the sequence of events here, right? So here we go. The contractor has just poured level 2, so the concrete is wet. It is not self-supporting. This is before the post-tensioning, and there's just formwork going down to the ground. And obviously that formwork just has to support the wet weight of the concrete. Nothing particularly interesting here. But let's fast forward in time just a few days to when that concrete cures enough for them to post-tension and then for them to go ahead and remove the formwork under level 2. You're going to get a situation briefly in time that looks something like this, right? So notice first off in the middle bay where the pore strip is, you have to put something called backshores. And these backshores have to go in before the formwork can be completely stripped. And the reason should be pretty straightforward here. You have 2 cantilever slabs, essentially, but the slab is not designed to be a cantilever. The slab is designed to be continuous through this bay. And so there's really no ability for the slab to self-support in this particular pore strip bay, right? And so that's the idea of backshores. And so I put here that the backshores will support 100% of the slab weight, but in the adjacent bays, and in fact in the typical conditions, you can strip that formwork and the slab is perfectly fine supporting itself at least for a short time. And then after the slabs go into this self-supporting mode, so they're allowed to deflect under their own self-weight, then the contractor is going to come back in and put shoring in those bays. Notice these are referred to as reshores, not backshores. Reshores simply mean that when you put it in place, you put it snug up to the underside of the slab, but the shores are not actually supporting the slab. So this is a critical difference, and I want you guys to really burn this into your mind here, the difference between a backshore and a reshore, because it's absolutely critical. And it's not something that engineers tend to be too familiar with, but we're going to see why this is very, very significant. So there we go, backshore versus reshore condition, right? Loaded versus unloaded condition. So now let's go ahead and pour level 3. So the contractor builds up the formwork and they pour the level 3 slab, which at this time is not cured, right? So obviously the forms up above level 2 are supporting 100% of the concrete weight, but look at what happens to your backshores on level 1. Notice your backshores on level 1 are now supporting the combined weight of level 2 and level 3. Again, that is necessarily the case because none of these slabs in this bay are self-supporting. They all rely 100% on the shoring system for support. In other words, there is zero stress in the slab. But that's not the case typically. Typically, you're going to have reshores everywhere else throughout the structure. Now here, they are designed typically for 100% of the wet concrete weight. In other words, the load goes through level 2 down to the foundation simply because that's the most the stiffest load path available. But in principle, the shores could be released slightly and allow your level 2 slab in those bays to pick up some of the load. That's why right here I put the slab, and then in brackets I put 25%, because in principle, those slabs in your typical bays have available capacity that could be used to support the wet weight of concrete above. And you'll see shortly that indeed they are used, just not necessarily here, but they could. So let's go up again one more level, and just to see, actually before we go up one level, let's strip the forms and then put back in the reshores again for level 3. So you can see the condition here. Once again, your back shores are 200% loaded on the lowest level, meaning that they're supporting 2 full levels worth of concrete slab self-weight. But your reshores, interestingly in this condition, at least for a short time, are not going to be loaded here. And the reason is because level 2 and level 3 are both supporting their own self-weight. So when the shores, once again, are put in at level 3, they're just put snug up against the underside of slab after the slab is already deflected. Okay, so let's go up another level and the predictable result. Once again, if you look at your back shores, you now have 3 levels of accumulated force on your back shores. And again, this is in the pore strip bay only where this occurs, right? So, gee, I wonder what's going to happen when we get up to 8 levels. And then look at your reshores. Again, that load is going to track from level 4 now all the way down to the foundation. But in principle, you could use the slabs to support maybe 1/4 or even up to 1/3 potentially of the wet weight of the concrete. So let's skip ahead several floors suddenly. So now we're up to, what is it, level 2, 3, 4, 5, 6. Okay, so the 6th floor just got poured, and exactly as you would expect, the back shores are now supporting every single one of these floors, and it's a cumulative effect going down the building. But the contractor at this point is actually able to remove the reshores on the underside of level 2, right? And so you could see how as you go down your building, your reshores support less and less load as they shed load into your completed concrete slabs. But the exact opposite, or something completely different, is happening to your back shores. That load is going to continue to accumulate down, right? And think about what we said early on with these pore strips. You want these to be open for an extended period of time, right? Something like maybe 8 weeks. Somewhere in that ballpark. 60 days is ideal. Now, contractors generally can pour, sometimes 1 floor per week. And so they're going to be up potentially 8 floors before they ever get to infill even this very first pour strip on the bottom. So you can see this is very burdensome to the contractor and also very, very critical in terms of this accumulated load. Now, this, I don't think, is readily apparent to structural engineers most of the time at the beginning. What percentage of contractors do you think understand this concept? The difference between backshoring and reshoring and how the load accumulates? I don't think contractors even tend to be very familiar with this. What you absolutely need is a professional structural engineer designing these shores for every building. Because you really need that kind of specialized knowledge to understand the nature of the backshoring here as opposed to the reshoring. Okay, and so this is kind of the critical insight that I wanted us to have when we return to that picture at the very beginning. So let's look at this picture. Again, you can see where the pore strip is, and immediately, I hope it's clear now that the backshoring condition at the pore strip was not properly done here by the contractor. Let me highlight what was and was not completed at this time, at least our best guess. you can see that the slabs in red are the ones that have not had the pore strip infilled yet. In fact, it's possible even one more of these was not infilled, but we're not 100% certain. But we have an accumulated force in that backshoring system of 1, 2, 3, 4 different slabs in red. And then we have just 4 slabs in blue resisting that. So remember, for a reshore condition, we need to utilize 3, sometimes 4 slabs to support the wet weight of just one level above, right? This is a hotel structure. The live load capacity is only 40 pounds per square foot. The slabs here were 9 inches, and so that's a little bit over 100 pounds per square foot of just the wet weight of the concrete. So you definitely need 3, if not 4 floors to support just one level. Here we have 4 floors supporting 4 levels. So there's actually a massive overstress condition in these slabs in blue. Now, if we look at the reshore condition, if you look over here to the left, for example, on this upper level, we have our formwork supporting 100%. And then we have 1, 2, 3 levels of reshoring coming down that dissipate load into the slab. So the contractor actually got the reshoring correct here. What they did not get correct, though, is the backshoring. And in fact, this is a very scary condition when you realize that a lot of accumulated load is coming down, and these shores are dissipating, similar to how the reshore condition would be. Now, it turns out in this particular project, there was no structural engineer who designed the reshoring and backshoring. This was just the concrete sub doing what they usually do. And sure enough, once they started pulling the forms from underneath these pore strips, it became apparent that there was some unwanted downward movement in the long cantilever. And there may have even been some slight uplift on the shore side, but this turned into a definite issue, and fixing it and adjusting it as we went up the building took a little while, and I think we got up another 2 or 3 floors before the effect finally disappeared. But of course, we had the contractor add in backshoring once we kind of realized what's going on here. I mentioned earlier that there's one additional reason to put the pore strips at the middle of your bay rather than at an inflection point. And this really illustrates the reason why. In the event that a contractor does not do backshoring correctly, you're going to start to see buckled shores. You're going to start to see slab movement, but at least it's much, much safer when you have this condition on the left. Generally speaking, the slabs are going to have some additional capacity to cantilever without there being excessive deflection, as opposed to the quarter point. If the contractor makes this mistake, you should be able to see that it's much, much more dangerous in this case. So this, I think, is really the strongest argument as to why a pore strip really should be at the middle of the slab. And of course, you absolutely need to demand that the shoring and backshoring is going to be designed by a qualified structural engineer, list it as a delegated design item, and demand that submittal prior to construction, because this is not intuitive at all. A lot of contractors, I think, are not really going to understand this unless if they've experienced this before. So what do you do if you get a call from your contractor one day and they say, hey, we don't know why, but these slabs are inexplicably moving down. We have it reshored 4 floors below, yet our slabs just deflect every time we pour them, right? If you get that phone call, you do not go to the job site to observe. You tell them immediately you need to go get every available shore and start putting these in all the way down to the foundation. Chances are what happened is they just missed the backshoring. So really quickly here, The pore strip alternative, known as the PS equals 0 system. This is a really nice system. Chavez Greaves, I think, we're going to start to use this as an alternative to pore strips. This guy can probably visit SEANM sometime. It's a nice system. We've used it now on 2 of our hotel structures is an alternative to the pore strip, and it seems to work really well. It serves the same function, so it's going to allow these 2 slabs on the left and right hand side to be post-tensioned independently and to move independently. So the construction joint here between the first and second pour is going to open up over a 60-day period or however long you specify. And then at the end, everything just gets grouted such that you have a continuous load path. Now, they can also design this system such that backshoring is not required. You just simply have to tell them to do that, and they will design this system to transfer moment through the joint such that it behaves very similarly to your typical bays as well. So this eliminates the backshoring condition and serves all of the same functions. And so far, it seems to be working really well for us. So keep that in mind as an alternative. And like I said, I think Chavez Greaves is probably, we're just going to start using something like this to avoid these issues altogether. That being said, there are special considerations here. So if you're using this system, everything I said about locating it at the midpoint no longer applies. This absolutely wants to be near an inflection point to minimize moment transfer, right? Shear transfer is easy. Moment transfer is much more complicated, especially if by definition your joint is trying to open up on you. So just some quick key takeaways here. I'm just going to show these really quickly. Pore strips are effective, but also burdensome with the time they have to be left open. The location within a bay has more to do with the construction considerations, not so much force and moment transfer. Shoring of the pore strip bay is critical, of course, and it must be understood by both the engineer and contractor. And then this alternative, such as a PS equals 0, offers a compelling improvement. And that's it. So I will go ahead and take any questions now related to the pore strips. Okay, and then the second topic I wanted to go over today is one related to stability bracing of columns. It comes from this particular project here. This is a 2-story steel frame structure. This is not a high seismic condition. So we have R equals 3 moment frames. Most of our moment frames are W24s. We had some 27s. But there's a few unique challenges associated with this building that kind of worked together to create a really unusual problem for us. First of all, this second floor is really, really tall. Floor to floor height in this structure is 36 feet, right? So that's pretty large in terms of floor to floor distance, right? But in addition to that, the second floor is extremely heavily loaded. So superimposed dead load here is something like 70 pounds per square foot on average throughout the whole slab. And then we have live loads generally of 60 to 100 PSF on this upper floor. Now, compounding this even further is not just the fact that the columns are very tall and that the loads are quite high, but also this is a very, very long span floor system. Level 1 under here is a gaming floor. And so the owner wanted to maximize and absolutely push the limit with our column to column distances in order to keep level 1 space as open as possible. So we have 80-foot floor girders, and tying into those are 80-foot floor beams. In our worst case, there's a few locations that are different, but very, very long span conditions. So you can imagine we have very tall columns with very, very heavily loaded conditions on them. Now, this is not a big problem for our gravity columns, right? A W14 by 311 can handle this type of condition pretty reasonably. But it's a different story for our W24 moment frames. So the problem we ran into is our moment frame columns are all failing just under gravity load combinations. So you run 1.2 dead, 1.6 live, and the columns fail. Now you run lateral related load combinations, and it's no problem sizing them in their strong axis. So provisions for wind and seismic drift, as well as strength, all of those are okay. We simply have this slender column buckling about its y-axis issue, and we have this all throughout the gaming floor here on all of our moment frames. I should note also that we could not size a W24 to handle this problem. If you look at the moment of inertias in the y direction of moment frame columns, there just aren't any available that work, right? So the question is, what do you do about this, right? How are we going to solve this problem? Well, one interesting suggestion that one of our engineers had was, hey, we actually have a ton of ceiling space here below level 2. Our ceiling is only at 18 to 20 feet on average. What if we go just a couple of feet above our ceiling and then we just interconnect everything with a whole bunch of beams in order to reduce the unbraced length of all of our columns? Okay, well, sounds reasonable perhaps. Let's put it in our software, run it, and see what happens. And in fact, this is a snip from our analysis model when the engineer actually tried this. And interestingly, we run it, and immediately all of the stress ratios go way down. Everything works. Our columns went from a 1.6 stress ratio to a 0.8 stress ratio. Everything looks beautiful. It passes the column provisions. It passes all of the lateral, seismic, and wind provisions. Problem solved, right? But I have to give credit to the engineer who suggested this. That same engineer actually discovered why this absolutely does not work. At least not in the way intended. So the question here, does this work? The answer is complicated and nuanced because there are some columns that may actually work under this condition. We'll get to some of those nuances in a little bit, but the idea itself of interconnecting everything at this intermediate level is both a misapplication of code provisions, and it's also a misuse of our software. And I'm going to explain why both of those statements are true. And you'll see this is actually going to outline an important pitfall that's very, very easy to make here. Okay, so in order to understand why this doesn't really work, or at least certainly doesn't clearly work as run through the software, let's do another thought experiment here. Okay, let's take a very simple steel frame, 2 columns and a beam. Everything is pinned. You have a diaphragm connected at the top that's laterally stable. So in other words, the columns are not free to translate at the top. They're pinned column conditions. The beam is pinned. So you got a simple K equals 1. And you clearly have an unbraced length of 40 feet in this column. Let's consider these wide flanges so that the columns have a clear weak axis and a clear strong axis direction. And now, for the sake of just a thought experiment, let's just load these columns together so that everything buckles and fails under weak axis buckling mode, right? So just considering gravity load, let's load this until both columns are failing, okay? So let's keep this condition in mind, and let's start adding a little bit of nuance and adding some questions to this frame. So now let's take the same exact condition, still overloaded in the exact same way, but let's introduce this intermediate beam at the mid-height of the columns, right? Very similar to kind of the idea for this case study, but simplified, right? So I want to ask a question. And again, you guys don't have to answer this, just think about it. Of course, if you want to shout out an answer, you're more than welcome to. But we add an intermediate beam, and here's the question. And in fact, this would be an excellent question, I think, for a PE or even an SE exam. What is the unbraced length of the two columns shown? It's clearly either 20 feet or 40 feet, right? But which one is it? The answer to this question is unambiguous and 100% clear, and I hope that'll be obvious here in a little bit. These columns have an unbraced length of 40 feet. That intermediate beam does not reduce the unbraced length of our columns. And there's two ways to explain this. I'm going to give you a good answer first. A good answer as to why this does not reduce the unbraced length is because it just does absolutely nothing to prevent these columns from buckling. If you think about the buckled shape, the only thing this is really going to do is force the two columns to buckle in the same direction. If neither of them had reserve capacity to begin with, neither of them can lean. They're not necessarily going to lean on each other. You're gonna just cause them both to buckle together. So this does not increase the capacity of your columns in any way. That's a good answer. The better answer to this question, though, is it is 40 feet because the intermediate beam does not meet Appendix 6 provisions for column bracing, right? It's really clear in the code what does and does not qualify as a brace, and this just does not meet those criteria. Therefore, this is not a brace for the column. So, going to the code, of course, is the best. The code is accumulated wisdom over thousands of structural engineers. And so the best thing to do in this case really is just to go to the code and check the provisions. But really quick here, let's say, well, what if the beam is not pinned? What if the beam is fixed? What's the unbraced length then? Once again, the answer is 40 feet. This is not going to meet Appendix 6 provisions, and you get the exact same buckled shape, so that does not help you. Well, okay, one more. What if we add diagonal bracing to this? What's the unbraced length then? It turns out here, the answer is 20 feet. There's a caveat there. You were assuming that the bracing system has sufficient strength and stiffness. So the diagonals, as well as your horizontal strut, and all of the connections, as long as all of those meet the requirements given in Appendix 6, you will have a braced column. And we're going to go into more detail and show you exactly why that is the case. Okay. So now that I may have confused you guys, let's go back to this original diagram here and just ask the question, well, how do you brace this column? Well, it turns out there are two legitimate bracing systems for columns. They're referred to as point braces and panel braces. Those are two sets of provisions. If you meet either one of the criteria given for those systems, you have a brace for the columns. Okay, and I should point out, point brace and panel brace, that is new terminology given in the 2016 version of the Steel Code, AISC 360. So if you have the Red Book or anything before the Red Book, it's not going to use this terminology. It's going to use nodal brace and relative brace. But it's the same exact thing. They just changed the verbiage to make it more clear. Here's a quote from the code as well. This is not Appendix 6, but this is in Appendix 7, which is one of the stability chapters of the code. And it says quite plainly and very clearly, bracing intended to define the unbraced lengths of members shall have sufficient stiffness and strength to control member movement at the braced point, right? And so think back to this joint A and joint B. It's interconnecting them, sure, but it's not providing any resistance to horizontal movement. So a point brace, first, let's define what that is. If we were to define what the code is saying is a point brace in terms of a picture, this would be it right here. You have a direct external resistance preventing lateral movement. So right here, this would be considered what the code defines as a point brace, right? So this point brace has to meet stiffness as well as strength requirements. There's very simple equations to calculate these and check them, right? But again, this is a critical difference. You're directly controlling movement with adequate strength and stiffness at a particular point, right? So point brace. Let's look really quickly at what the code means by a panel brace. So the panel brace is a little harder to state, but still not too unclear. It prevents the horizontal movement of the braced point, in this case, point B, also point A, with respect to the adjacent brace points. Also along the same member at points E and F, those are braced, right? Those are pinned supports where it's not able to translate. And so I dashed in a deflected shape that's really being restrained, right? It's not allowing the point A and B to shift laterally in that way. And so it has sufficient strength and stiffness against that type of movement. And so that then qualifies as a panel brace. And again, it must have adequate strength, it must have adequate stiffness, and the equations are pretty straightforward. And so you can immediately see, whether or not your system counts as a brace with these criteria. So really quick, knowing now what a panel brace is and what a point brace is, let's look at just some really interesting configurations here. Okay, and again, this would be a really good SE question, maybe even a PE question, but consider this frame here. Now, let's just say that column A has sufficient strength to do whatever we ask it to do. It's got plenty of axial capacity, it's got plenty of flexural capacity, it's very, very stiff, etc. So column A and then column B is unchanged, like we have. Well, what are the unbraced lengths of column A and column B in this location? So I'll give you guys just a second to think about this. And let's go ahead and look at the answer here. Well, column A has an unbraced length of 40 feet, where column B has an unbraced length of 20 feet, right? So in other words, column B is able to lean on column A, where column A provides that external support to column B, right? And of course, you have this bracing force applied to column A. In order to prove that this is the case, you have to apply that load at the brace point and show that column A both meets strength requirements and also does not deflect enough. In other words, meets stiffness requirements as well. So there you have it. Column B would be braced in this condition. Here's another kind of interesting configuration that you could have potentially. So notice here we have columns that are very strong in one direction and much, much weaker in the other direction, such as W24 moment frames. And if you look at how each one of these columns can lean onto the strong axis of another column, if these columns have sufficient strength and stiffness, every one of these columns would indeed be braced at the elevation of these beams. So just kind of an interesting, application of these requirements, so to speak. And this gives a little bit of credibility to that original idea, right? Because we're interconnecting everything above the ceiling. Some of them might actually be braced because of an effect similar to this, although it should be pretty apparent that the software is not going to automate this. Now, I said something really, really scary at the beginning of this segment. I said that we put those beams into our analysis model we ran the analysis model and everything passed. The stress ratios went down immediately. But I hope it's clear now that simply putting those beams in there are not going to count as brace points. So in reality, a lot of these stress ratios should not have gone down, yet it did in our software. And this is really kind of the scary big idea I wanted to bring up. Oh, really quickly here, this kind of demystifies, at least for me, why it is that top and bottom chords of trusses are considered braced at each of the panel point, at least braced in the vertical direction here. It certainly does not brace them out of plane. But you have what qualifies as panel bracing for these green dots on the lower diagram. Maybe those are more nodal braces. But I just remember, being told early on that you just call these things braced in the major axis or the vertical direction at each panel point. But now it's clear why, because the code specifies exactly what a panel brace is, and these are generally going to meet panel bracing requirements. So back to the software. Really quick, here's just an interesting webinar from AISC on this exact topic here. So these slides will be available to anyone who wants them. Here we go. The software. This is what really caused me to choose this exact topic here, because our software could easily be tricked into thinking that a column is braced when in reality it is not. Okay, so this is RAMSS, what we use, and apologies to anybody who uses eTabs or any other program. I really don't know if this is a problem or not in other software, but this is definitely an issue in RAM. If you take a simple gravity model like this, these are 40-foot tall columns, and you put an intermediate beam in there, is RAMSS going to think that those two columns are braced at 20 feet? The answer is yes. By default, RAMSS is going to pin or laterally brace, I should say, every column that has a beam framing into it, regardless if that beam is actually connected to some kind of lateral support that restrains it. So RAM is always going to change the unbraced length in this condition when you add the intermediate beam. Now you can override it, but you cannot change that default setting. So in this case, what you would have to do is go into the column module and individually pick a column and tell it manually to remove that brace point. So you can do that, but it's not automated. So think of the potential pitfalls that we have just based on this fact alone. I hope this scares you guys. It certainly scares me. And this is absolutely something that needs to be taught to every one of our engineers coming in when they're first learning the software. This is just some output from RAMSS. So you can see right here the unbraced length is 20 feet. You can see it's sized it as a 1499, and you can see the stress ratio is 0.98. But that, of course, is not what's happening. In reality, it is 40 feet unbraced length. The ratio and the strength goes way down, and the stress ratio more than doubles in this case. So you better know and understand how your software works, especially because it's not too uncommon for us to have an intermediate level here where maybe we're adding some framing in to support some kind of equipment or something. We got to be careful to make sure that we're not tricking our software into thinking that there's brace points when there's really not. Similar condition happens in our finite element software. This is RAM elements. This is a correctly configured condition with the correct unbraced lengths. I make one tiny change to the model, and suddenly the unbraced length goes down to 20 feet. You can see all I did was I broke the columns at the nodes. It turns out RAM elements is going to, by default, consider every end of every member to be laterally braced, as well as not just braced for column considerations, but even for beam type of provisions, it will consider it a brace point. So one thing we tell our younger engineers, in regard to this program is if you have a physically continuous member in real life, you're generally going to want to have a continuous member in our software as well. So you could see, once again, this is a very, very easy pitfall to fall into. So some key takeaways here, just let you guys kind of read this on your own. That concludes the presentation. So I will go ahead and take any questions now.